Okay, good morning. I think you can hear me. Hey, good morning, everyone. Okay, today we'll discuss mathematical induction. You learned this in high school, I believe, okay? But perhaps the depth may not be enough. So I will discuss this very important technique for proving mathematical statements for natural numbers. Again, okay, to remind you in case you forgot. I will give you a few examples, subtle examples. You can read many straightforward examples from textbook. It's rather straightforward. But I will give you a few examples that are not that straightforward. You have to be careful when you use mathematical induction. So I'll give you a few examples to illustrate these things, all right? So everyone knows that mathematical induction is used to prove a statement for natural numbers. We want to prove a statement P of n for natural numbers, for all natural number at least n naught. Can be 0, 1, or something, okay, a small number. All right, for example, we want to prove that summation of first all the numbers equal n squared, for example. This statement Pn. We want to prove it for all n at least 1. All right. So what we do is there are two steps, two main steps and two important steps. Both of them are essential. One is called the basis step. We prove the statement holds for few initial values. Very often, we only need to prove for P naught, but sometimes it's not enough for a single value. We need to prove it for some values, for first few initial values. All right? So in this particular case, n naught will be equal 1. So we only need to prove this one holds for n equal 1. So of course, very often this is trivial. Usually it's trivial, but sometimes it may not be trivial, depends. But for almost all cases, this one will be trivial. But this step is very, very important. It's extremely important. We'll see, okay? Then the next crucial step is called induction step. We assume this statement holds for all natural number up to n minus 1. So from n naught up to n minus 1. Then we want to prove that under this assumption, that's called the induction hypothesis. Then we can show that the statement also true for n. Okay. Now here is we only need to consider n is more than nt, because for these we have showed it already up to nt. So here we only need to work on numbers more than nt. Then for each such number, we'll prove that statement holds for n whenever it holds for n naught up to n minus 1. All right. Typically, this will be called strong version of induction. In high school, perhaps you only learn that we assume that this one is true, then imply this one. But these two are really equivalent, but not matter. Okay. We can always assume everything here is true, not only this one, but also up from n naught. All right. So that's called the mathematical induction. And this is a crucial step. Now, the key step actually is to get a recurrence for Pn in terms of these, P naught up to Pn minus 1. So the crucial step, the most important part of mathematical induction, actually to obtain a recurrence relation for Pn based on previous n minus 1 statements. That's the most important part. Once we get that, remaining thing typically are very simple manipulation. Very simple, I have to quote. Sometimes it may not be trivial, okay? But basically some manipulation of algebraically or otherwise, we do some manipulation to get this result. Typically, it's rather easy compared to this one. The key step really is to get the recurrence for Pn. All right. So that's the basic idea of mathematical induction. So for this particular example, what we do here, we assume it's true for n minus 1, then we prove it's true for n. So for this particular example, induction hypothesis so that's our assumption. This induction hypothesis. Now we want to prove this one holds. So under this assumption, we want to prove this one holds. Typically, it's very easy. Typically, most example in the book it's very easy. It's rather straightforward. So what we can do is this one. For example, for this one can be rewritten as so summation up to n minus 1. So one term is here, last term is here. Now we just use our assumption here. So induction hypothesis for this one give us n minus 1 squared plus 2n minus 1. Then simple manipulation of this one, of course, will give us n squared. So that's finish our proof. So you see, it's very, very easy once you get the place. All right. But there are quite a few subtle things about mathematical induction, and one have to be very, very careful. As I said, both steps are extremely important. Basic step and induction step. Okay. What induction step says is suppose we have the following situation: you climb a mountain or climb a ladder to the heaven, for example. Okay. Okay, climb the stairs or ladder to heaven, maybe. Okay, up to the heaven. Okay, there's a ladder of steps or does not matter. So what this one says, regardless of where you are, somewhere. So if you are here, this step always guarantees you can go one step up. This one guarantees you can always go one step up. Induction step guarantee, regardless of where you are, you can always climb one more step. So that ensures you can keep on going up to the heaven. All right. Now, the basic steps is very important. Now, even with this condition, you have to be somewhere in the ledge or in this stair as a step, somewhere in the stair or upstairs, this stairway or whatever. Okay. So you have to be somewhere. If you are here, even if you guarantee this, you cannot get to the heaven because you are not somewhere in the step. So this one guarantees you are somewhere in the step. Maybe you are initially you are here. So then together with this one, it guarantees you can keep on going up to the heaven. All right. Okay. So both steps are very important. And I will give you a few examples for this one to illustrate some subtle points when we use mathematical induction, especially when we use it to prove correctness of algorithms. Because for computer science, it's very important. And it's this extremely important tool for computer science students to prove correctness of algorithms. Oh, sorry, I forgot my glasses. Cannot see what's going on here. Let me see. Oh, so far so good. Okay, so I'll continue without my glass. Okay, because it's easier for me. I'm nearsighted and getting old as well. Farsighted as well. All right. All right. I will not discuss many examples in the textbook. All of them are rather straightforward. I will just discuss a few examples to illustrate a few important things you have to be careful. All right. Of course, as I said, recurrence. Once we have recurrence, that's become very easy. For example, for Fibonacci number. So that's Fibonacci number, all right? We want to prove that suppose we want to prove the statement. This Fibonacci number looks very, very innocent. It's very easy to compute it, but actually it grows very fast. Initially, you cannot see it. So even up to here, it does not seem to be grow very fast. It may look to be innocent, but actually it grows very fast. It grows exponentially. It grows exponentially. If n equals 50, the number is huge. 100, you forget it. You cannot get it. All right. If we use recurrence to compute 100 Fibonacci number, you forget it. Any computer will not give you answer. If you just use this one directly, I'll get back to this one later. Okay. Now suppose we want to show that indeed this number grows exponentially, so it's at least 1.618 to power x. By the way, this is called the golden ratio. Okay, so that's the first 4 digits, our golden ratio. That's a very important ratio. It has many, many applications. You will see, even in stock market, you will actually it's related to this golden ratio, movement of stock market. Okay, how accurate it is, I don't know for stock market, but quite often if you listen to people talking about stock market, you will see golden ratio. It's related. Okay. Anyway, suppose we want to prove this one for Fibonacci number. All right. So let's see. The most important step, as I said, is induction step. So let's work on induction step first. Okay, induction step. All right. So it's quite easy. We assume this one holds for n-1. Everything up to n-1. So we assume that typically we'll say that for any k fn, fk, so for this induction hypothesis. All right, in the induction step, that's the induction hypothesis. Now we want to show that this one still holds. So we want to show that this one still holds. So as I mentioned, the key important step is the consideration of fn, how fn is based on previous values. In this case, it's trivial because we know it already. All right, so we can use this one directly. So what we know is fn equal fn-1 plus fn-2. Now use the induction hypothesis here, so we can obtain this one is at least 1.61 here n-1 plus 1.618 n-2 by using induction hypothesis. That's where we use induction hypothesis. So in the induction step, somewhere we have to use it, and we need to use it in order to get our conclusion. All right, so that's what we get. Now, let's pull it up. All right, so we rewrite this one as this. So this one becomes all right. It turns out this one is just slightly bigger than let's see. Oh, let me see. 1.8. Oh yeah, it's bigger. Okay, it's bigger. This one is so here it's 2.617,924. Oh, it's not big enough. Oh yeah, it's big enough. Okay, this one. 1.618 squared is 2.617924, I think, something very close to this one. It's less than this one. All right. So this one is bigger than the squared. So therefore, we can say all right. So this one indeed holds. From induction step, we can infer that indeed this one holds, assume these two. That's the induction hypothesis. All right. Now, can we say that we have proved it? Actually, this one is false because it does not hold for the first few ones. So that's illustrates the importance of basis step. The importance of this step. For example, when n equals 0, f0 equals 0, but f1, I found it, this one. So this one does not hold. 0 is not more than 1. So actually it failed for the first one. It also fails for this one and this one, I believe. So that's the importance of basis step. Without it, we may get a long conclusion. Okay. Now, but we can prove this one is in this order. Let's say just 1/3, okay? Instead of square root of, actually close to square root of 5, the bottom part. But then let's say just 3 equals 1/3. Now, this one indeed holds. Initially, actually, this one does not hold, but this one indeed holds. This one does hold. Induction step will be same. Just with 1/3 here. All right. So everything is a 1/3, but the manipulation is same. Everything is same. So induction step will be same. Basically same. We get it. Now, the remaining thing is for the initial part, the basis step. Actually, sorry, no, this one has to be 1, not 0, of course. 1. Because otherwise 0, of course, but not hold. Okay. For 1. All right. Now we can verify that F1 equal 1, right? F2 equal 1. So here we can compare it. 1, 6. Here's 1, 1/3. Here's 1, 2. So of course, this one roughly 0.8. I mean, not 8, okay, 0.5 something. Something, okay? So this one roughly 2 point, this one is 0.8 something. Okay, now this one more than, no less than this one no more than this one. So for initial one, basis step, we can see that it holds for n naught. So here n naught is 1. But is this good enough? Actually, in this case, when t will equal 2, we need to verify it for both n equal 1 and 2. And this one is not enough. The reason is the value of this one depends on 2 terms, previous 2 terms. So for these 2 terms, their value needed to be determined. It cannot be determined by previous ones. So that's initially for this one, 0 cannot matter. Okay, we can ignore it because it starts with 1. Okay, because in induction hypothesis, we want to get conclusion for this one from previous 2. But now for the first one, so this one depends on previous one, it's not there. This one depends on previous 2, it's not there. So in this case, here, this one can be ignored. Okay. So for these, we need to verify it for first 2. So for basis step, actually we need to do it for 2 terms instead of 1. All right. So terms actually, how many terms do we need to verify in the basis step? Depends on the recurrence relation. Because if the recurrence relation for Pn, typically we have n tend to be sorry, no sound? Oh, sorry, there's sound. Okay, that phone call, I just ignore it. Okay. Okay, I thought no sound. For the calculation, here's the t. I said mt. Just t is okay. Because in definition of the calculation holds for n at least t, and more than t. Now we have to do it for first t terms, for n naught, n1 up to t. Did I write nt? If I write nt, then maybe in this way. So nt. No need, it should be t. If I wrote nt, then it's better in this way. So up to t. Okay. All right. So for example, if I have the following recurrence relation. All right. Now, if this term depends on n-1 and n-3, how many terms do I need to verify for the basis step? So I will start with maybe n here, n equals 0, 1, 2, 3, 4. So here a value of a term here depends on this one and this one. 2 terms. So only 2 terms, but it's up to n-3. So in the basis step, 2 terms are not enough. We have to do it for 3 terms. So that's basis step. Okay, so that's very important. Basis step is essential. We have to do it for a few terms, and number of terms is determined by recurrence relation. All right. So in the definition of the recurrence relation, so here in defining it has to be n at least 3, or at least 3. So then we have to do it for 3 terms, for 0, 1, and 2. Okay, so here is a very important step, is basis step. So it's typically trivial, but we have to do it, and it's extremely important. We cannot ignore this, otherwise we prove nothing. Otherwise we prove false statements, okay? Yeah, enforce this important step, let's take a look at this Fibonacci number again. If we change the first 2 initial terms, then we give totally different term. If we start with 2, say -3. If we start with this, then we still use this recurrence. We form a new sequence, but it's totally different. It will be -1, -4, -5, and so on. So that's a sequence. If I start with maybe 5, 0, so will be, you will see it's totally different terms. So the recurrence alone is not enough to uniquely determine property. A property will be determined by recurrence together with initial conditions. So therefore, the basis step is extremely important. Okay, you will see it's important again later on when we do other things. All right. Okay. As I said, the most important step in mathematical induction is the induction step. Actually, the key part is to obtain the recurrence. That's the most important part and the most difficult part. Okay, so let me give you an example. Suppose we have a chessboard. I decided 2 to power n, 2 to power n. So the reason use power n is because just for simplicity. Otherwise, it's okay. But in this case, we do need it. Okay, sorry, we do need it. Okay, because we evenly divide it. So it's a chessboard. Let's see. Okay, so I could just draw a part of it. Okay, the statement is, suppose 1 square is missing from chessboard. It can be anywhere. So our claim is for all n, we can always cover it by L-shaped tiles. This L-shaped tile consisting of 3 squares. Regardless of where I remove 1 square out of chessboard, we can always cover it as far as it's a 2 to power n by 2 to power n chessboard. So that's a statement we want to prove. Okay, so that's statement Pn. We want to prove that statement for all n at least 1 natural number n. All right. So in this case, actually, so induction is written in this way: basis steps and induction steps. Actually, in the roadmap, it works backwards. We have induction step. You have to think about induction step first, then decide what's the basis step. What do we need for basis step? So roadmap actually starts with the consideration with induction step. Actually, we should start with finding a recurrence for the statement first. So in this particular case, what we'll do, you will see importance of this number will be power of 2 because we'll divide the board into 4 pieces. So that's why we need power of 2. Okay, otherwise it cannot be evenly divided. So what we do is divide the board into 4. So then each will be of dimension 2n minus 1 by 2n minus 1. All right. Now we try to find recurrence for Pn in terms of smaller ones. So that for each piece, it will be Pn minus 1 in this case. All right. Now we remove one piece. So in this particular case, this part, one piece is missing. So that's Pn minus 1. We can assume this part can be exactly tiled with this one for this part because it's missing one piece. But for these 3, it's not. We cannot apply the induction hypothesis directly because no piece is missing. So what we do is put an L-shaped tile here in the middle. So then divide into 4 pieces. Now each piece will have one piece missing. Okay, so here will be also Pn minus 1 holds on this one. Here also Pn minus 1. Here also Pn minus 1. So Pn now depends on the 4 Pn minus 1. So we know all of them satisfies because each piece we see one square missing. All right, so this piece can be entirely tiled with this one. So are these 3. So the whole strategy is use a strategy for these 4 pieces together with this one. So we can fully cover the whole board. All right, so you see how it works. Below the map is really to start with recurrence relation, find the recurrence relation first. All right, now what's the initial condition? We'll see initial condition is 4 pieces, a board with n equal 1. So 2 by 2 board. So for this one, if one piece is removed, it becomes this tile. Of course, it can be always done. So it's very trivial. So if this piece is missing, so this is L. As I said, typically the basis step is trivial. Typically it's trivial. But we have to determine what are needed for basis steps. That may not be trivial. All right, so in this case, it's simple. We only need this one. Okay? All right, so just basic idea of mathematical induction reflects your memories. Okay? All right. Okay, I'll give you this recurrence. Actually, this recurrence comes from one problem mentioned in the first week, I think, when we want to find both minimum and maximum element. So that's number of comparisons when we use divide the count technique. All right. So we know that T2 equal 1 and Tn satisfies this recurrence relation. Now for simplicity, because each time divided by 2, let's just consider the case that n is power of k. I thought power of 2 to make things easier. All right. So we want to prove that statement we need to prove is all right. We want to prove in number of comparison is at most 1.5n. Remember? So that's actually from there. So let's forget the background. Just from this the consideration, we want to prove this mathematical statement. Tn is at most 3n over 2. All right. So of course, in this case, basic step, we can see actually just this one. Later on we'll see. Okay, we only need to check this one. So of course, it's satisfied. So that is 1. If we replace n by 2, we get 3. Of course, it holds. Now for the consideration, so inductive step or induction step. So what we can do is very simple. So Tn, using this the consideration is at most 2 times Tn over 2 plus 2. All right. Now what we do is use induction hypothesis for this one. For this one, induction hypothesis for this one. All right. So replace it by 2 times this one. So 3n over 2. Right? So we use induction hypothesis for Tn over 2. So we get this one. So what we get? Very simple. 2 clauses, we have 2, 3. Unfortunately, it does not work. We want to prove that Tn is at most 3n over 2. But if we do this, what we get? We can only prove that it's 2n over 2 and 3n over 2, but plus 2. We cannot get rid of this one using induction hypothesis. Because in this case, very simple. What else can we do? We cannot do nothing. So it's just this one plus this one. Nothing's wrong here, but unfortunately, we're not able to prove it. All right, so how can we prove this one using induction? So that's one type of subtlety when we use induction. Sometimes we need to prove something stronger or more general. Sometimes we need to prove something stronger or more general. So in order to prove this one, actually we prove something stronger. So this one is not enough. So our purpose is to prove this one. All right, that's our purpose. But in order to prove by mathematical induction, what we will do is instead we prove a stronger statement. We prove something stronger. The reason is it works. Because this one cannot work when we do induction step, but this one works. All right, of course, in order to prove this one, we need to do 2 things. One is for induction step. So let's see, induction step. All right, so induction step, what happens here? So let's use that one, okay? So now this one, we use this one instead of this one. Induction hypothesis is this one. All right, minus 2. Okay, so that gives us 3n minus 4 plus 2. So that is 2. So see, now this one works for the induction step. So sometimes actually we need to prove something stronger. There was another example in the notes, but I will not discuss it. Maybe later on when I discuss graph theory, I will discuss that example about Orleans cycle because it's more involved. Okay, so that also requires to prove something more general. Okay, now of course, then we need to check the basis. All right. Now in this case, base step it still holds. Does that hold? Sorry, something's wrong in basis step. Then we may have to change the statement a little bit to. Oh, sorry, n equal 2. Oh, sorry, it still holds. Okay, n equal 2. I'm thinking of 1. Okay, n equal 2. So it's just equal 1. Base step holds because n equal 2 here, not 1. Here n is 2. I was thinking of 1. Okay, so 2 is just 1. Tn equals t. Based on this one, t2. So this holds. Okay, because it's 1 here. It's 1 here. Okay, so it's indeed holds. So that's this example indicates in order to prove a statement, sometimes we may need to prove something stronger. Of course, for you, usually you will not see this type of situation. But keep in mind, sometimes we may need to do this. All right. Okay. Let's see time. Perhaps I should stop now. Yeah, only it's 14 minutes already. Okay. So let's have a break. After break, I will discuss 2 examples of using mathematical induction to prove correctness of algorithms. That's very important for computer science students because how can we be guaranteed that your algorithm really works correctly? Testing, debugging can never prove the correctness of algorithm unless your algorithm only works for small number of examples. All right, it can only help you to find bugs, test the debugging. Find the bugs, then you can debug it. All right. So after break, I give you 2 examples dealing with correctness of algorithms. All right. So see you in 15 minutes.